Welcome to a journey through the strangest mysteries of our universe. From eerie radio silence across the cosmos to time-bending twists and even black holes devouring reality itself, we're diving into questions that challenge everything we think we know. How is it possible we're still alone in a universe this massive? What happens to time if you can travel through it? And does reality change just by looking at it? Join us as we uncover the wildest paradoxes in space, each more mind-bending than the last. Let's explore the unexplainable. Have you ever looked up at the stars and wondered if we're truly alone in the universe? Given the vast number of stars and planets out there, it seems almost certain there should be other intelligent civilizations. This question is at the heart of something called the Fermi Paradox. Back in 1950, physicist Enrico Fermi casually asked, "Where is everybody? If the universe is so old and so massive, filled with billions of stars and potentially habitable planets, why haven't we seen any signs of alien life? In theory, even a single civilization could colonize the galaxy in just a few million years. So why is there a deafening silence?" There are some intriguing explanations for this paradox. Maybe advanced civilizations self-destruct before reaching out to the stars, like by exhausting their resources or engaging in destructive wars. Or perhaps they're out there but avoid us, following a kind of cosmic prime directive to let developing civilizations evolve on their own. Another theory? We might just not be looking in the right way or have the technology to detect them yet. The signals they send could be in forms we don't recognize, or perhaps they're using communication methods far beyond our understanding. And of course, there's a possibility that we are indeed alone, or the first. If true, that means the responsibility of the universe's intelligent life lies with us, and what we do next could shape the future of the entire cosmos. Imagine if you could go back in time and change the past. Maybe prevent a major historical event, or even just tell your younger self to make a different choice. This idea fascinates people and has led to one of the biggest mysteries in science and philosophy, the time travel paradox. One of the most famous examples of this paradox is the grandfather paradox. Picture this. If you traveled back in time and prevented your grandparents from meeting, you would erase your own existence. But if you were never born, how did you go back in time to make that change in the first place? It's a loop that seems impossible to resolve. Scientists and theorists have proposed some mind-bending explanations. One is the idea of parallel universes, where changing the past creates an entirely new reality. So, by preventing your grandparents from meeting, you would create a universe where you were never born, while the original timeline, where you exist, remains unchanged. In this view, there are potentially countless alternate realities for every possible outcome. Another theory involves closed time-like curves, where time behaves like a loop, allowing for past events to happen in such a way that they're consistent with future outcomes. In this case, time travel wouldn't actually allow you to change history because events would unfold in ways that align with the timeline you're in. This might mean that any attempt to alter the past would ultimately result in events that somehow keep the future intact, preserving a self-consistent timeline. Then there's the possibility that the laws of physics themselves might prevent time travel from ever happening, or at least from creating paradoxes. Some scientists believe that time travel into the past might be theoretically impossible, or that the universe has a way of correcting any paradoxes, a concept known as the chronology protection conjecture. The time travel paradox challenges our understanding of time, reality, and cause and effect. Whether time travel is theoretically possible or just a thought experiment, it pushes us to explore some of the biggest questions. What is time, really? And if we could travel through it, would we be masters of our fate or prisoners of paradoxes? Have you ever noticed how people change their behavior when they know they're being watched? This phenomenon is at the heart of the observer's paradox, which suggests that simply observing something can alter its natural behavior. Originally, the observer's paradox was explored in linguistics and social science. For example, imagine trying to record people speaking in their natural dialect, but the moment they realize they're being recorded, they start speaking more formally. So by trying to observe their natural speech, the observer unintentionally changes it. But this paradox isn't just limited to human behavior. In quantum physics, it gets even stranger. The famous double-slit experiment showed that particles of light, called photons, behave like waves when unobserved, creating an interference pattern. But if you observe which slit each photon goes through, that pattern disappears and the particles start behaving more predictably like particles. It's as if the act of observation forces these particles to decide on a state, which challenges our understanding of what reality really is. This has led to theories that observation might actually influence the fundamental nature of reality. Some interpretations suggest that reality doesn't settle into a definite state until it's observed, meaning that consciousness might play a role in shaping the physical world. This idea has inspired countless philosophical debates about free will, the nature of reality, and whether the universe needs an observer to exist in any definite way. The observer's paradox reminds us that observation isn't a passive act. It can influence outcomes, shift behaviors, and even alter what we think of as reality. Whether we're talking about recording someone's accent or tracking particles in a lab, the observer's paradox shows us the surprising power of awareness and the delicate relationship between the observer and the observed. The double-slit experiment is one of the most mind-bending experiments in the history of physics. Imagine this setup. We have a screen with two slits, and we're shooting tiny particles, like electrons or photons, toward it. You'd expect the particles to go through one slit or the other and create two bands on a detector screen behind them, right? But that's not what happens. When both slits are open and nobody is observing, the particles act like waves, creating an interference pattern on the screen, just like ripples in water that overlap and create complex patterns. This result suggests that each particle travels through both slits simultaneously as a wave and interferes with itself. But here's where it gets strange. If scientists set up a detector to observe which slit each particle actually goes through, the interference pattern disappears. The particles start behaving like particles instead of waves, passing through just one slit and creating two distinct bands, exactly as expected if they weren't interfering. So, what's going on? It's as if the very act of observing the particles forces them to choose a definite path, changing their behavior from waves to particles. This has led scientists to question the role of observation in quantum mechanics, and even whether consciousness itself can affect reality. The double-slit experiment doesn't just challenge our understanding of particles, but also shakes the foundation of what we think reality is. It suggests that at the quantum level, reality isn't fixed or objective. It's influenced by whether it's being observed. This experiment has sparked countless theories, from parallel universes to the idea that consciousness plays an active role in shaping the universe. In the end, the double-slit experiment leaves us with a profound mystery. Does reality even exist independently of observation, or is the act of observing fundamental to what we experience as reality? One of the biggest mysteries in theoretical physics is the black hole information paradox. It starts with the idea of a black hole, a region in space with gravity so intense that not even light can escape. When a black hole consumes matter or energy, the information about that matter, like its properties and structure, should be preserved somewhere in the universe. This is a core principle in physics. Information cannot be lost. But here's where the paradox comes in. Stephen Hawking proposed that black holes actually emit radiation, now called Hawking radiation, which causes them to slowly evaporate and lose mass over time. Eventually, a black hole can completely evaporate, leaving behind nothing. If a black hole vanishes without a trace, what happens to all the information about everything it ever consumed? According to classical physics, that information would be lost forever, which breaks the fundamental rule that information is conserved. This is the essence of the paradox. Does information truly disappear when a black hole evaporates, or is there some hidden mechanism we don't understand? Physicists have proposed various theories to solve this paradox. One idea suggests that the information is somehow encoded in the Hawking radiation itself, though exactly how that would happen is still unknown. Another hypothesis is that the information might be stored on the black hole's event horizon, a concept known as the holographic principle, where the three-dimensional information of everything falling into the black hole is encoded on its two-dimensional surface. The black hole information paradox has sparked a fascinating debate, pushing scientists to explore deeper connections between quantum mechanics and general relativity. It challenges us to rethink our understanding of space, time, and even the fabric of reality itself. So does information truly disappear in a black hole, or is it waiting for us to uncover it? The answer could fundamentally change our understanding of the universe. These paradoxes remind us that the universe is as mind-bending as it is vast, and that there's so much left to explore. From the Fermi Paradox to black hole enigmas, each question leaves us wondering, what's really out there? If you enjoyed this journey into the unknown, don't forget to hit like, subscribe, and keep an eye out for more videos that push the boundaries of what we know. Until next time, keep looking up and stay curious.